Hello, good afternoon. You hear me? Thank you. Thank you for responding. So today we are going to start our sensor. Okay. So sensor is a very wide topic. So I just give you a feeling. Let's go to Google. Okay. So let's put the sensors here. Okay. How many? That's a lot. 1 billion, 1.6 billion sensors. Okay. But if you go to Science Direct, by the way, from April 1st, our whole UC system get back the subscription of Elsevier. So Science Direct is a website I use almost on a daily. So I suggest everybody check. You can do advanced search, okay? Say for example, article within the article we have sensor. So let's see how many things we are going to get. Last time I checked, it's near 1 million. So near 1 million. So these are all peer-reviewed journal articles, okay? Journal articles. So from here, you can also check, sort by, let me do this. Sort by relevance. It's also, you can sort it by date, okay? By date. So sort by date. So you can see every year how many. Every year, last year was 80,000. This year we just started. It's already 45. So it's increasing every year, right? So it's a huge amount. But if you go to another site, it's called ieeeXplore. I put in sensors here. So what I'm going to get. So I'm going to get about 500,000. Okay, that's also a big number in ieeeXplore. Okay, so these you can find many of the sensor papers you want to read. So you can put the relevance. You can try newest, oldest, most cited. Let's check most cited, what they say. So people quote the previous ones. So to your surprise, what are the most cited one? It's called compressed sensing. Okay, so you have too many sensors, too much information, how you compress it, okay? Compress. Then sensor networks, or the sensors talk to sensors, okay? All right, and so on and so forth. This is a classic paper. I read this one. I did something on this one. It's called a camera calibration. Camera is a sensor, right? So you have sensors everywhere, right? You have your eyes is your sensors. Your nose is your sensor. Ears are your sensor. Your tongue, taste, okay? And your skin is also sensor, like touch sensor, okay? Also temperature sensor. Your fingers can check with it. So it's just too many things, okay? Too many things. So sensor is a very wide subject area. You want to read more, you just go to Google. So like, let's say, what is the top sensor? I just searched it. So what is the top sensors like here? So this one will give you a category about the top journals, like Nature Electronics, like Sigma. This is KDD. This is remote sensing. Satellite is also sensor, right? Satellites also sensor. ACS stands for American Chemistry Society. Sensors, actuators, and so on and so forth. So sensor is a very wide topic, okay? very wide topic. So of course, we cannot go through all of them. So today, I'm going to do some basic background about sensors. Actually, there's another term, it's called transducers. So we are going to learn what are the differences, okay? What are the differences? So what are the types of the applications of measurements instruments? What is generalized configuration of measuring instruments, okay? So as you know that we have 60 students in the class, we are going to do 6 different types of sensors. I do not limit the sensors to be related to mechatronics. You can use other sensors, okay, like chemical sensors, molecular sensors, whatever, or nano sensors, what types of sensors. I do not limit that related to mechatronics. It could be something else, not necessarily mechatronics, okay? But on the other hand, mechatronics is already broad enough. All the systems with mechanical part, with electronics, with control systems, with computers is called mechatronics, okay? So we are going to talk about the general introduction of sensors today. So in the next 2 weeks, we are going to cover sensors and actuators. So we'll see how much we can cover, but it does not matter. Whenever you need to study some of the sensors, you have to focus on that and learn the basic principles. So that's why we call this is a foundational course for mechatronics. In our textbook, okay, there's a very good coverage about sensors and actuators. Okay, let's move on. Okay, so of course, here I am going to cover most on those measurement for controls. So we have 3 purposes here, why we need to measure, okay? Why we need to measure. So there is a very interesting, saying that, okay, let me make my comment box out so I can draw. There's a very interesting saying that if you cannot measure, you cannot what? If you cannot measure, you cannot what? Fill up the, yes, you cannot control. Actually, there's another term. They don't use control because control is actually very narrow. What they say? You cannot manage, okay? Okay. So if you cannot measure, you cannot manage. That's so true, right? Yeah, it's so true. But specifically here, we talk about manage the system's behavior. So it's control. You cannot measure, you cannot control, of course. Yeah. So 3 purposes that I'm going to talk here. The first, measuring for what? Measuring for monitoring the process and operation. Sometimes in measuring this one is simply to check if it is healthy. So when you visit a doctor will be measure on you, check your heartbeats, temperature, you know, and you sometimes check your eyes, you know, and check your ears, nose, and you know, and pat on your back. All these are just kind of measurement. So measurement, you as a system, whether the system is in good shape, in good operation, is healthy or not. So is there something wrong? Okay, so this kind of a fault. Is faulty or not? Okay. So measurement is for monitoring and for understanding the health. The second is to control the process and operation. So control, we should understand in this case is called feedback control, okay? We don't say feedback anymore. It's actually talking about feedback control. If you don't use this one for feedback, then you measure, then what is feedback? You use that measurement for control, is already feedback, okay? So for example, okay, in the end of the class, you are going to receive emails asking you to do a course evaluation. That's actually a sensing, okay? Sensing on basically like to check how Professor Chen was teaching, okay? And then measure that and give me feedback. I read those feedback, I will improve so that the whole Mechatronics course offering will be constantly got improved in feedback control. Make sense? So so the measurement for control, okay? Measurement for control. So control, of course, measurement is important. But on the other hand, sometimes this is from our engineering point of view, okay? Our engineering point of view. But from science discovery people, okay, do a basic science. They also do lots of experiments. They need to measure that. So they do the sensing and the measurements for discovery, okay? Sometimes if you cannot sense properly of some quantity, then the lore is still getting hidden. You cannot discover it, okay? So I suggest, I don't know how many of you pay attention to the recent discovery of muon. How many of you noticed in the news a week ago, the discovery of the muon measurement? Yeah, great, nice. At least you have one. Then Google something, read it, okay? This measurement do not, okay, align with the traditional theory. So people are very excited. This is yet to be confirmed. They are doing more measurements to confirm we need new physics. All existing physics are not going to work because of the muon behavior cannot fit in, okay? So measurement for discovery, experimental analysis. So I think I already said everything, monitoring, control, and so on and so forth, okay? So there are a lot of things you can monitor, like temperature, pressure, flow, okay, voltage, current, flux, many things, physical quantities, okay? Okay, so for this sense, you do the measurement. Some of them is, you cannot measure it directly. So you have to infer from other measurements. So this is actually called soft measurement, okay? So, but it's still considered as a measurement. So you measure something else and use those together, you infer what's going on, okay? What's going on. So that's called soft measurement. Then you need to do this, how to synthesis or mix all the information together and get some useful information out of it, so that you need to use artificial intelligence here, right? Yeah, so there are a lot of things interesting there. Control processes and the operation, we said a lot about it. So it is one of the components in the control loop, control system, okay? All right, so for example, aircraft system, industrial machines, and or the oil refinery, and so on and so forth. When you drive a car, there are lots of controls going on. There's also lots of sensors, measurements going on, okay? One of those is your odometer, okay? what distance traveled. Okay. All right. So we'll go back to this odometry story. So this is a picture for a feedback control system. Okay. So you have a CV is a control variable, MV. So MV and CV is control variable. Why? So this is your control, and you have disturbance can come into here or come into here. Okay. Then control director, you have a desired value and control variable. So it's called set point. You already use this SP, set point, reference signal. And effector means take effect, or it's called actuator. Okay. Actuator, you should think it broadly, okay, broadly. So, so say for example, you have crop duster. I use this on is a UAV crop duster. You spray those fertilizers, or you spray pesticides. All those things are, to me, is a effector to change the behavior of the crops so that they are not subject to the pests influence. Okay, that's also a feedback control system. Okay, that's an actuator. Okay, but the fly the drone to see everything is growing well, that's a remote sensing. It's also a sensor. So a drone can be used as a sensor or as a actuator. Okay, so I already said that experimental engineering design. Okay, so you understand the nature of the object. Okay, do experiments. So experiments and theory, they should cross-validate. Okay, sometimes they do not agree, then there's something going on we don't understand it yet. So that's why you need basic scientific research. It's called science. Actually, we are engineers. Okay, our job. So I don't know whether you know what is engineering. What is engineering, by the way? Okay, if you got a bachelor degree of mechanical engineering, and they say, "Oh, what is engineering?" You cannot say it briefly in the layman's language. You're in trouble. Engineering is to get things done. Okay, get things done under constraints. So that's the answer. Okay, that's the answer. Then if they want you to elaborate, you tell them more. Get things done. Yes, it's a creating something, building something. You know this maker movement. So there was a movement talking about having a maker, 3D printers in every community. So if you want to make something, you can go and make it and share the workshop. That idea was good. Anyway, okay. So we talked about the reality and theoretical model and measure and verify. So we talked about Box-Jenkins models, and Box, okay, GEP Box is a British statistician. He said famously, all models are wrong. Some of them are useful, okay? All right, so with the model, you can use the pen, paper, or computers. Today's Simulink, okay? And then you have Simscape. So, but you still need to decide what are the parameters of the model. So how you get those parameters right? You have to do experiments, okay? Then check from the experiment, then you fit that kind of thing. So today, we actually call this is a digital twin, and a real system you measure. so that digital twin and the physical twin, physical twin, and then you have a behavior matching, okay? Behavior matching. So this is something when you talk about digital twin, then you should be able to explain, say, hey, how the behaviors is matched to the physical twin. Okay, keep asking that question. Okay, I need further study. All right, so sometimes the monitoring, control, and analysis, they probably are intertwined, not like totally separated. Okay. So extremely common for our today's engineer, including the machine or process in the design phase, okay? Design phase. So you know how to do the computer programming, click mouse. Yes, they are important, but consider that is only a component, okay? So they are not that critical in that sense, okay? So those components external to the computer, sensors, actuators, are more often the limiting factor in the system design. So we are going to study how the sensors, if not properly chosen, we are going to, is going to limit our design, okay? So you heard about that, so you have a bucket. So you have how much water you can put in is determined by those, the shortest block, okay? So sometimes the sensor becomes the bottleneck because it's not accurate enough, then the overall system cannot be good enough, okay? So at this point, it's good to take a look of general configurations and functional descriptions of a measurement instrument. Do you guys? I think all of you use the multimeter, right? Okay, multimeter. Multimeter is something you used for measuring a resistance. Some of them can help you to measure capacitance as well, to measure DC and AC and so on and so forth. Okay, but you can see anything you use, okay, anything you use, okay, anything you use, it is kind of instrument. So instrument is something built on top of sensors, okay, sensors. So if something, say this is a sensor, so it's usually not enough, okay? The sensor alone is useless. Let's say that way. Sensor alone is useless. You have to wrap up the sensor from an instrument point of view. So what are the essential components there, okay? So we're talking about measurement instrument, okay? And with the instrument put together in a system, you have equipment, okay? And what are the building blocks, okay? So let's talk about this by focusing on those functions, okay? Then we decompose the whole big instrument into different parts, okay? So if we know the different parts, then it's possible we can synthesize building a new combo of different elements. Then you have different types of new and useful instruments, okay? So as you can see that in your iPhone, okay, so your iPhone, this is a new generation of instrument. If you say, oh, this is can be used as a timer, can be used as to count how many steps you walked. You can also do the vibration yeah, and timing, many other applications based on the sensors within the phone. Okay. So this is the picture I want you to take a look. Okay. So we are talking about functionality, not just physics. Okay. So this is called functional elements of an instrument. So when you have an instrument, you should have all these blocks. Okay, more or less. Some of them may be omitted or combined, but you should have these things. So we're going to see examples on that. Okay. So as a user, like imagine you are using a multimeter. So there you should have a display, right? So that you as a user, that you have a data representation element, okay? Then it's possible you can save and storage, save the results, play back. So this is a typical like oscilloscope. So usually you can memorize the measured, so you can save it. Okay. So then you have data transmission element. After that, you have a variable manipulating element, a variable conversion element, then primary sensing element, and you have a measurement media. So this is the quantity you want to measure. Okay. Okay. So maybe you look at this one. I never thought about for a piece of instrument we have this functional blocks. Okay. But let's take a closer look. So let's take a look. So primary sensing element. So these are descriptions. It's boring. Let's look at the example. Then we come back and see it. So this is let me do this. So this is a pressure. This is the pressure gauge. So this is you, user, and this is your eyes. You watch this one, you'll see this pointer can go up and down. So this thing is called a scale, okay? Or we call this a calibrated scale, of course. You can calibrate that. Then later on, this scale points, you should trust it, right? So how this scale will go up and down, there's a pivot point in here, okay? And this one will go up and down. But this one is a linear motion in here. So this is a spring. So this linear motion up and down. So then you have a pressure. So this is a fluid. So the fluid goes through this hole. So this is a pipe, okay? So this is the pipe, okay? This is the pipe, okay? So I want to see what's the pressure in there. So we just get this instrument attached to it. So, so this fluid will go to here and push this piston and go up and this is a rod, okay? And then this is a spring, okay? So you can see that. However, if we use this picture to check the chain of variables, will be like this. It's fun. So the first one is measurement media. What's the measurement media? The media is the liquid, okay? Media is the liquid, fluid in here. So then this is a quantity of interest that we want to measure, which is measured quantity. We want to measure the pressure in here. So the pressure here will go through a piston. This is the piston. So it's called primary sensing element, is the piston, okay? And then they will have, it's also serving as a variable conversion element, meaning I convert my pressure to the force, okay? To the force here, okay? Then this force will go through a data transmission element. In this case, it's a piston rod, okay? Piston rod. And with piston rod, you have force. Then this transmission element will turn the force and make, this force will make the spring. The spring is like a variable conversion element, turning the force into displacement. So, you know, force is proportional to the displacement of the spring. So that force will through the spring becomes a displacement up and down. This displacement will go through a variable manipulation element. It's called a linkage. So this is a linkage. Becomes a motion of the another type of motion, linear motion versus rotary motion, rotational motion. Then later on, we do a data presentation element. It's like how to display this. This is the pointer and the scale. Then finally, it's presented to the human as a user looking at this. So this whole process is a nice illustration of the pressure gauge. Functionally, we can decompose it in this chain of transformation. So when you see this scale indication of the pressure, it already has gone through a series of those conversions. Make sense? As an engineer, you should have a pretty good ideas about this, all this, what's happening behind. It's good for you, you should know, okay? At least you learn mechatronics, you should be, especially mechanical engineering, you should be able to explain this one in this functional representation way, like showing in this picture, okay? In this picture. So if I give you an instrument like this, is it possible you just explain or draw this diagram for me? You should, okay? You should. Of course, you need to read more to understand the working principle, right? So, okay. So we're going to continue. So this is another example called a galvanometer, okay? So probably today you don't see this very often, but previously it is a lot. So you can see the like earthquake, you have a plotter moving very fast, write down all this. So this is also similar, okay? So the media is air, voltage to be measured, okay? So this voltage add on to this one, okay, will provide you with excitation of the voltage supply for this coil. So if you have different voltage, then the coil will turn. Then when coil is turning, then there's a light source, okay, hit to this mirror, okay? This mirror will reflect this light beam in here. And the light beam in here, this is a piece of paper, maybe it's in a roll. It's rolled in a row, and the roll is moving, okay? Slowly moving. So because of this one this paper is a special paper. It's called photosensitive, okay? Photosensitive. So whenever you hit this paper, you are going to leave a mark. But if you move slowly, this mark will become different as the voltage is also dynamically changing. So this becomes like recorder, analog recorder of the curve for the voltage time variation, time history, okay? And the whole thing, this is a permanent magnet to give you the permanent magnet field. So then if you have a voltage coming, it will generate a motion, okay? Generate motion. So these are the basic functional elements. I hope you can recognize the basic functions for the successful operation of this instrument by doing something similar in here, okay? So here we are very basic, but this one we have more working principles behind it, okay? So I think we have explained about data storage and playback. Some of the, so this is just a representation. This is a presentation, like a visualization or display of the signal you are trying to measure. Okay. But today you have lots of digital measurements. You can store all these digitized using an analog to digital converter to record it. Okay. So in a nutshell, we should have a general classification of sensors and transducers. I'm not sure in your dictionary, do you have this term, transducers? Transducer is to convert one variable to another variable. Is that right? Yeah. Transducers could be a sensor, could be an actuator, in fact. So you change one variable to another variable, right? So, but anyway, transducer here, we just say this is sensors, okay? So two general classes. One is active, another is passive. So in simple case, you say passive means I don't need an external power supply. I don't need an external power supply. But if you active means you need a power supply, like op-amp, transistors, okay? Op-amp and transistors, these are active sensors. But otherwise, it's called passive, okay? Passive, okay, passive. So the resistor, inductor, capacitor, diodes, and transformer, okay? Transformer, okay. Of course, transformer is to transduce from one variable to another variable. Here, let me give you an example. So this is my resistance. We measure the resistance, okay? Why we call this resistance is a sensor of what? Remember, if you have temperature, okay, different temperature, the resistance will be different. There's a temperature coefficient. So you should check this one out. So when at a different temperature, the resistance is different. So that's one thing, temperature. Sometimes under the light sensitive, or sometimes it's not like pressure. You have those load cell. It's also checking is because of the resistance is going to change according to pressure, change to temperature, and change to light, the photosensitive light, the resistors, diodes, or so on and so forth. So, so don't just say, oh, a resistor is not a sensor. This could be a sensor, okay? Active and passive, you should be able to tell. If there is an external power supply, then it's active. But but sometimes you may feel like I have a sensor in here, and the sensor will be able to generate electricity. You don't need to have a power supply to it. So then it is passive. Okay. There's another classification. So I told you either is active or passive. Another one is called analog versus digital. Okay, digital. We have learned how to sample FT to F star. Okay, so digital mode. The analog signal, you can quantize it to sample it into digital form. But why digital? Okay, why digital? So digital is like, this is a TTL logic. TTL stands for transistor logic. Okay, so it's level on is like from 2 to 5 is all considered as on. 0 to 0.8 is all considered as off. So 0 and 1. Okay, 0 and 1. So therefore, you can see this is actually very robust to the noise. So if you have some noise just within the threshold, no worry. Okay, no worry. Okay, so with some wide range that matters. So it means the precision of the signal of not the importance. So in other words, in digital form, it is more kind of like immune to noise. Okay, it's kind of a noise immune. Okay, so digital usually is like that. So tolerant to the noise. Okay, tolerant to the noise. And it could be really accurate if you use many bits. Okay, can be 8-bit, 16-bit, 30 bits. Today's computer usually is operating at 64 bits. Okay, I used all of them from 8-bit. Okay, so just a little bit of history if you are interested in Google. People may ask, oh, what's your first microprocessor you played with? So mine is Z80. Mine is, I started with Z80. You can Google that. Okay, what is Z80? Let me check. I'm curious. Oh, it's still here. So it's Z80 is 8-bit microprocessor. Yeah, it's familiar like this. By the Z-Log, 1974. Okay. Interesting. See some history. And I think today we don't construct our AD and DA ourselves. We just buy the existing chip. So in my time, sometimes we need to do the AD/DA ourselves. So we know what's the inner principles of AD and DA. In our textbook, we do have explanation about how AD/DA was realized inside the chip, the working principle there. It's better to take a look. Okay. Then this is a very interesting figure you should know about. From you have a piece of sensor, a piece of instrument, you measure it. So you should know that what you measured here, okay, what you measured here, what's behind that? So what's behind that? So towards here, towards the left, you should understand that this output is corrupted by two parts. One is due to interfering input and IM, okay? This is interfering and IM. Okay, what is IM? It's something modifying it, distortion. Another one is output component due to the desired input and IM. So desired output, so we'll go through some sort of function, transfer function. So there's nothing ideal, there's nothing perfect, okay? In the sensor case, you should always remember, nothing is perfect. The sensor is not perfect at all. The sensor readings, you should always put a question mark until you investigate and exclude those factors. Basically, the question is, can you really trust the sensor? Is the sensor telling the truth? How do I know it's telling the truth? Okay, you should always put that kind of question mark. But I hope you understand, behind the sensor signal you got, inside or internally, you should consider there are three types of modifying inputs in there. One is called modifying inputs, one is called interfering inputs, one is called desired inputs. So there's transfer function. These are all transfer functions in here, okay? So we are going to explain this one, and then we will stop today's lecture earlier. I got a meeting at 3:30, so we are going to be on 15 minutes earlier today, sorry. So let's go through that. What is the desired input, okay? So those are the quantities we specifically intend to measure. It's called desired input, okay? It's this guy, ID, okay? Interfering inputs, those are the quantities the measurement is unintentionally sensitive to. So this is II, interfering. So this FD, FI are input-output relations. We didn't say this relationship is static or game. It could be nonlinear. It could be dynamic, okay? Okay. So we are going to see an example. Sometimes it's a differential equation, it's a transfer function, okay? So we're going to see an example later, okay? What is the modifying inputs? These are the quantities cause a change in the input-output relationship from desired and interfering inputs. So itself is cause change in this relationship, okay? How they affect this one is shown in this one. So you have modifying inputs going through this one, add on top of this one, going through this one. So let's see an example, okay? This example is an interesting example. So now you can see that what is the desired input? This strain, the strain of this part, okay? Strain of the part. So if I apply force to stretch it, then here, this is a strain gauge. It's supposed to give you a change, okay? A change in the resistance, okay? In the resistance. So, but the question is, the strain is a variable. We cannot measure it directly. We do not know it's proportional to this or not. So it could have some nonlinear relationship, okay? So there's always source of uncertainties, okay? Sources of uncertainties. So the specimen may not be the same. So if you change another one, it's different, okay? So this is a strain gauge setup using a bridge circuit, okay, bridge circuit. So I put the resistor RA, RB, RC. The RC you can tune. It's a potentiometer. So then you can check what is the output in here, the E0. So the E0, okay, is the output voltage based on the EB. EB is the supplying voltage, okay, voltage. So this epsilon is something we want to, the epsilon is something we want to measure, okay? Then this is kind of like, according to material, it's proportional to the strain. So these are proportional coefficients. Then you have change in this G, the RG. RG is a strain gauge resistor, okay? So the RG is strain, the resistor, then this is a coefficient, GF, okay? So, so the RG, delta RG, okay, is this value. We put in here, okay? Then this is RC, this is the RG, origin RG, RA, so RA, this is also RG. So the output here is not zero, okay? It's not zero. So we can tune that one into zero, okay? This is called balance. So if you do not stretch it, just stay as is, natural position, then I can tune RC to see the Z0 is 0. So when E0 is 0 means there's no strain, no stretch, okay? No stretch. When you have stretch, then the E0 is not 0 because this RG changed this little bit, okay? That little bit will be reflected on the E. The bridge is no longer balanced, okay? It's not balanced. So with that, we identified the three things of this picture. The interfering input, that's easy. Say for example, you are in a room, so you always have this type of 60 Hertz alternating current field at home. This is electromagnetic, say for example, from light bulbs, lights. So those are frequencies. So those are interfering inputs, okay? Those are the interfering inputs, 60 Hertz field. And also you have different temperature, different humidity, then this behavior is also different, okay? Okay, so this is the interfering inputs. What is the modifying inputs? What if your battery is not full, its battery is low, the battery voltage is not accurate? And internally you have some temperature change, okay? Say if you heat this guy, this specimen, then everything you measure is actually drifted, is different, okay? So that's called modifying inputs. So now you have an idea about when you have a sensor, you got a reading E0, then you should know what's happening behind, okay? What's happening behind. So you should know interference and perhaps internal modifications somewhere, okay? So let's go back. Whenever you have a sensor, don't trust it, okay, until you verified it, okay. I have a thorough understanding of this picture of sensor is good, okay. So this is an example of those desired input, interfering inputs, and modifying inputs, okay. So we have another example called the YouTube manometer for differential pressure measures, okay. So this is a marked ruler, okay? This is a ruler, okay? This is a ruler fixed in there, okay? I fixed the ruler in there. So I have a different, well, I can measure the surface, okay? I measure the surface. The difference of the surface is called X, okay? We use this difference to infer what is the difference between the pressure P1 and P2, all right? So yeah, very nice. Direct inputs, I want to measure P1 and P2, okay? But there are lots of possible interferences. Say for example, you have some shaking and the table is shaking, you know. So your table is not flat, leveled perfectly. So then there's some tilt angle. Those will affect your accuracy, right? So modifying inputs like you have temperature, in a different room temperature, the expansion coefficient of the liquid is different, so it's different. You have gravitational force. Say, for example, you measure the thing in this height above sea level versus going to a very high mountain. I think the readings will be different. And so on and so forth, okay? So whenever you use a sensor, you really need to identify what are those inputs, okay? What are those inputs? Otherwise, you'll be in trouble, all right? So we give two examples to show that characteristics of sensor uncertainty sources, okay? So again, let me say one more time. Don't trust the sensor unless you have enough evidence you can trust, okay? Otherwise, don't trust the sensor in general, okay? And a lot of times, you didn't spend time to verify the sensor. Then in the end, your performance is not good, everything is working, but it's not working nicely. And in the end, you find out, that's because of the sensor. I thought it's accurate, but it's not. So give you the trouble. Will bite you in the later stage of your project. So you better in the beginning, you understand the sensor, these are inputs, interfering input, and modifying inputs. Okay. So, but what we can do in front of that. So how we can nullifying or reducing those effects of the spurious inputs. So there are many other methods. So you most recent ones, it's like, oh, how about I do some filtering? How about I do some compensation about the opposing inputs, cancel it out? How about we just get output, then make corrections to it? If you know the table is tilt, instead of you solving the table leveling problem, that's maybe very expensive. You just live with it. So after I got the readings, I do some corrections, giving the information I know I have some tilt level. So another idea is talk about sensitivity. We are going to dive right to the sensitivity. Okay, the sensitivity is you have a sensor, you measure X, you get a Y, right? So Y is kind of like f of X. Okay. Okay. So then I want to understand at a nominal value x0, if I change, put a delta x in here, okay, then what is delta y? Do you know how to do that? I think this is you learned from calculus, right? So delta y is what? It's f prime and delta x, right? Right? Okay, we should stop here. And we are going to talk about those sensitivities. I think you should be able to do this quiz questions, okay? Then we start next week on more on the sensors, okay? Starting with sensor sensitivity. Yeah, as I said, I have to stop here. I'm joining another meeting. All right, so any urgent question? If not, I'm going to stop sharing and say goodbye to you. Oh, we got 40 students show up today. -1, it's 39. Not bad. Thank you. I'll talk to you later. Bye-bye. Enjoy the sensing.